Hello, we're going to start off today's presentation by defining a force. What is a force? Well, fundamentally, a force is a push or a pull. You push something or pull something, you are applying a force. And in terms of its consequences, forces cause acceleration. So it causes acceleration and it's a push or a pull. Unit is the Newton, spelt with a little n because it's a unit, not a person's name in this context. And it is a vector quantity. So to remind you, a vector quantity means that it has magnitude and direction. And like any other vector quantity, it can be split up into two smaller vector quantities. All vectors can be split into two. So if you have a force F at angle theta, then you can split that into two components, Fy on the y-axis being F sine theta and Fx on the x-axis being F cos theta. Okay, so given that very brief introduction, what is a force? Let's look at some types of forces. Weight. Weight is the action of gravity. The force that an object experiences is called its weight. All objects that have mass, which is pretty much all objects, if they're in a gravitational field, will experience weight. The actual value of that weight depends on two things. It depends on the strength of the gravitational field, little g, which on Earth, on average, at the Earth's surface, is about 9.81 newtons per kilogram. And it depends on the mass of the object measured in kilograms. And the equation is W equals mg, so the weight, in newtons remember, equals the mass times the local gravitational field strength. Where do we measure that from, or where does that force apply? Well, it applies to all parts of the ball, but what we do is we say that it appears to act, and this is one of the geniuses of Newton's, he was the person who worked this out mathematically, it appears to act from what we call the center of mass or center of gravity. When we're drawing an arrow to represent a force as a vector, we need to think about the length of the arrow, which is the magnitude, the direction, and the point of application. Where does that arrow begin? So in the case of weight, you should try always to draw that arrow starting at the center of mass or the center of gravity of an object. The second type of force, which is often created as a consequence of the weight, is the normal force. Now, the word normal traditionally in English means at 90 degrees or at a right angle. And that's because the normal force, or the normal force is called the normal force because it acts at a right angle to any two touching surfaces, touching objects. So the ball is resting on the surface, and the normal force, we have to draw it relative to that surface at 90 degrees. It's a reaction force, okay? If you take away the weight, it isn't there anymore, which is equal to the pushing force to a limit. Why does it exist? Well, if you put the ball or any other objects on a surface, then you're compressing the top of that surface. As it's compressed, the bonds, the intermolecular and interatomic bonds, you're squeezing them, they push back. They want to return to their original length. Each bond only pushes with a tiny amount of force, but there are millions and millions of bonds. So the combined total force is the normal force, which matches the weight force so that the object is in equilibrium, it's not moving. That's to a limit. Obviously, if you push hard enough, then you can overcome that repulsion and sink into the ground. Notice that the normal force only equals the weight when the object is on a horizontal surface. If it's not on a horizontal surface, if it's at an angle, then it will be a component. It will be the component of the weight that is at right angles to the surface. The logical consequence of this is if you increase the angle to 90 degrees, then the normal force disappears completely, which makes sense because at 90 degrees, the block or the object is no longer actually in contact with the surface. It's just going to be falling down. So the equation is N, normal force in newtons, equals mg, the weight, multiplied by cos theta, as shown on this diagram. In this diagram, you see that the girl is leaning against the wall, and in this case, the normal force is actually a reaction to her pushing into the wall. So again, it's just a reaction force. Again, it's at 90 degrees to the surface, and again, the normal force equals the pushing force, and again, up to a limit. In other words, if a wall was weak or the girls applied to greater force, then the normal force would go to the limit, and then it would collapse the wall, not the girl. Well, the girl with the wall, presumably. Another type of force is tension. Tension is a force that is experienced by stretching an object. So we commonly think of a cable or a rope, but it could be any object that's being extended or stretched as opposed to compressed. Tension is always really existing in a pair. As you can see in this diagram, assuming there's no acceleration, then the tension force balances with the other forces that are involved. So the person pulling the rope exerts a force on the rope, and the tension force is opposite to that. Similarly, the tension force is therefore pulling on the object, and the object is pulling on the tension on the rope. So it all works out in nice force pairs. We'll be talking more about force pairs in a later presentation. Another type of force is fluid or air resistance. Fluid resistance, a fluid is defined as anything that flows, so that would include gases and liquids. Another shorter word for these things is drag, which again applies both in liquids, water normally, and in gases, air normally. And again, it's a reaction force, and it's created by relative motion between the object and the surrounding fluid. In other words, if a submarine is sitting in the water not moving relative to the water, then there is going to be no drag. But once it starts moving, there will be drag. Similarly with the airplane in the photograph. The airplane is travelling at a velocity from right to left, therefore the friction force, but air resistance force, acts from left to right. It is a kind of friction force, but we try to separate the two terms. So friction, when I'm talking about it, really just refers to the contact force between two objects, which we'll look at in a minute, and air resistance, fluid resistance, refers to the resistive force due to passing through a fluid. The magnitude of that force depends on the relative velocity of the object and the surrounding fluid. It depends on the cross-sectional area of the object, all other things being equal. It also depends on the shape of the object. So if I replace the front of the airplane here with a flat disc, same cross-sectional area, same relative velocity, then the air resistance will be much greater. And of course, it also depends on the fluid itself, the density of the fluid. Water has a much, much greater resistive force than air, simply because it is much, much more dense. What is it caused by? Well, if you imagine instead of the particles of air or the particles of water, you have little balls, then the force required by the airplane to push away those balls, as it needs to push them away, then they exert a force on the airplane or the submarine or whatever. And it's exactly the same with air particles. Yes, air particles are very, very small. Each particle only requires a small amount of force, but there are millions of air particles. Upthrust. Upthrust is experienced by any object when it's immersed in a fluid. Normally we're talking about water, but occasionally we're talking about air as well. The basic principle was discovered by Archimedes, and it was that upthrust is equal to the weight of the fluid displaced. So, if the density of the object is less than the fluid it replaces, then the upthrust will be greater than the weight, logically, and that has consequences. For example, for a submarine. If you make the submarine less dense than its surroundings, then the upthrust will be greater than the weight. So a submarine can fill its tanks with air, releases compressed air, changes its density, the upthrust increases and the submarine rises. If a submarine wants to sink, it opens the vents, lets in the water, the density of the submarine increases and the submarine sinks. Similarly with a hot air balloon. Hot air is less dense than cold air. So by heating up the air inside a balloon, the density of the balloon entire decreases, the upthrust is greater and it rises. Spill some of that hot air, let in cold air, the density of the balloon increases, the upthrust decreases, and the weight brings the balloon down, decelerates the balloon. The final force we're going to look at is friction. It's a very important force. Friction resists the relative motion of solid surfaces. Remember the difference with drag, with fluid resistance. The relative motion of solid surfaces against each other. In the case of the picture we have in front of us here, the object is moving. It has a velocity down the slope. In that situation, you have dynamic friction, and the friction always opposes the direction of motion. In this situation, where a person is pulling on a rope attached to an object and there's no motion, there's still friction. There has to be, as we'll see in a later presentation, because there's no motion. So the forces must be balanced. Okay? That kind of friction is called static friction. Static because there is no motion. The maximum value of static friction is given by the equation static friction force equals the coefficient of friction, μs, multiplied by the normal force. That's the maximum value of static friction. Okay, because the static friction force will match whatever the pulling force is, so the overall forces are balanced, but it will match it up to that value. Those are the terms. Notice that coefficient of static friction, therefore, equals the frictional force divided by the normal force, so it's a ratio. And as a ratio, it does not have any units. Dynamic friction uses exactly the same equation. And that's really because by having this number, coefficient of static or dynamic friction, we're kind of hiding all the detail. That number is fundamentally dependent on the exact surfaces. So it's a very empirical relationship. We're not predicting anything here. We're actually just giving you a number that we've measured on previous occasions. So for any set of circumstances, grass on concrete or wood on tile, there will be a particular value of static friction and a particular value of the coefficient of dynamic friction. And the coefficient of static friction is always greater than the coefficient of dynamic friction. It is easier to move something than it is to start it moving. It requires a greater force to start something moving, but once it's moving, actually you require less of a force to keep it moving. Okay, so before I go, here's a quick question for you. Where would you draw the friction force vectors in this picture? There's air resistance, yes, there's drag, but we're not interested in that. Where is the friction between solid surfaces and what direction is that frictional force pointing in? For your answers, refer to your textbook or come and ask me. Okay, thank you very much.